Hey everyone, it's Bradley Bush with another algebra video for you. Today we're talking about systems of linear equations in two variables. Since we're in two variables, that means we are in two space, so we see an XY coordinate plane on the right. Our to-do list, we'll have a quick review of systems of linear equations in two variables, so you kind of have an idea of the background, what it is we're dealing with. And then the core of this video is the substitution method, which is one of the two methods used to solve these types of systems of equations. I also will put a list of all of the video elements with their timestamps, so if you want to skip around to whatever is interesting to you, you're more than welcome. Let's start. So, what is a system of linear equations in two variables? Sounds kind of nasty, but if we break it down, it really is not bad. The two variable part just says that we've got two variables. We've got an equation and it has two variables in it. Generally, these two variables are x and y. They're linear, so you have linear in this definition. That just means that all of the variables have exponents that are 1. So those are implied and you don't see them. So we'll never have an exponent that's not 1 on any of the two variables. And a system just means we have more than one of these equations. Because we have two variables and they're linear, the exponent is 1, that means this equation represents a line, and we have two of them, so we've got two lines. That's it. So it sounds complicated, but it's not. Here's an example. These two equations, equation 1, I label my equations with numbers with circles around them, so you can tell that it's equation 1 or equation 2. And these two equations represent two lines, and a solution to this system would be any point that is simultaneously on both of these lines. So in mathematics, we call that a point that satisfies both equations simultaneously. So if you plug in the xy coordinate to both equations, you get a true statement mathematically. But really, it just means that the point is on both lines at the same time. So you have three different options for solutions. You have one solution case where you have these two lines and you only have one place where they cross. These never turn around. These lines never turn because by definition lines are straight. So you can have one crossing, you can have no crossings because the lines are parallel, or you can have infinite number of touching points because the lines are on top of each other. They're the same line. So any point that's on one line is also on the other. How do you know which of these options you're in when you're given a system? Well, simple. You just start solving the problem. And if you get an answer, then you're in option 1 where you've got one solution, as long as you've done your algebra correctly. If you start solving your problem, and your variables drop out, and you're left with just numbers and an equal sign, you look at that equation, say, is this a true statement or is this a false statement? If it's a true statement, that means you've got infinite solutions. You're in option 3. And if it's a false statement, like 0 equals 2 is not a mathematically true statement. So you know you're in the option number 2 where you have no solution. How do you solve these types of systems? Well, the two main methods are substitution and addition. And this video focuses on substitution. I have addition videos in my algebra playlist if you want to check those out. So the substitution method, the main idea for the substitution method is that we're trying to get rid of a variable because we have two variables. We want to eliminate one of them and then solve for the remaining one. And then once we have one of the variables known, we just plug it into the equation and solve for the remaining one. So I've got two examples here, one on the left and one on the right, and we'll start with the one on the left. So we have a system here. We have equation 1 and equation 2, and we want to solve the system using the substitution method. So we'll want to pick one of the equations and solve for one of the variables. If I'm looking at it, I see this variable right here, the y in equation 2, that's all by itself. So why don't we just choose that? We could choose any variable to solve for in either equation, but I just choose the easiest one. So let's solve for y in equation number 2. So I have equation number 2 down here copied. And let's solve for y. So that means we take 2x to the other side. And what do we get? We get y equals negative 2x plus 1. So now we'll take that y equals negative 2x plus 1, and we'll plug it back into the other equation, equation number 1. So we solved for y in equation 2 and plugged it into equation 1. So equation 1 looks like 3x plus 2y, there's a y here, equals 4. But instead of having the y, we're going to plug in the negative 2x plus 1, because that's what y equals. And now we just solve for x. So let's see what we have. We probably should distribute the 2 through. And what do we have? We have 3x plus 2 times negative 2x is negative 4x. And 2 times 1 is 2 equals 4. We have the 3 and the negative 4x give us negative x. Plus 2 equals 4. If we subtract 2 from both sides, that gives us what? Negative x equals 2. Let's multiply both sides by negative 1. And what does that give us finally? Well, that gives us x equals negative 2. So we've solved for x, right? So x equals negative 2. Now let's plug that back into equation 2, or we could have used equation 1 and solve for y. So here's equation 2, 2x plus y. There's really should be an x right here, but we know what x equals, so let's plug it in. X equals negative 2. And now 2 times negative 2 is negative 4 plus y equals 1. That's kind of a terrible negative 4, huh? Let's add 4 to both sides, and that gives us y equals 5. So now we have an x and our y coordinate. So our solution then is the x is negative 2 and the y is 5. So that's the point that touches both lines simultaneously. In other words, that's the point where the two lines cross. And if we looked at a picture of this, we can see the graph here, equation 1 and equation 2. And where do they cross? Negative 2, 5, just like we found algebraically. So that's the first example. Let's look at the second example. We have our system right here. We have equation 1 and equation 2. We need to solve for one of the variables. This x looks like it's a low-hanging fruit, so let's do that. So we have equation 2. Let's solve for x. So we will add 2y to both sides. Not sure why I put that negative there. Sometimes things just come out and you don't know why. So we have x equals negative 3 plus 2y. We can plug that in now, so we know what x is, right? X is negative 3 plus 2y. We can plug that in to 1. 1 here is 5 times y minus 4. Whoops. That's supposed to be an x. 5 times x minus 4y equals 9. Instead of having that, we're just going to have negative 3 plus 2y. And now we're going to solve for y. So let's distribute the 5 through and solve. So what do we get? Well, we have 5 times negative 3 is negative 15. 5 times 2y is plus 10y. We have our negative 4y, and we have our equals 9. The 10y and the 4y give us 6y. I had to think about that for a second. Equals 9. Let's add both 15 to both sides. What does that give us? Getting close here. 6y equals 24. One more little step, divide by 6, and we have y equals 4. So that's nice. We have found one of our values. So we have y equals 4. Now we take that and we can plug that into equation 2. So we had equation 1, solve for one of the variables, and we take that and we can plug it back into equation 2 or equation 1. Actually, it doesn't really matter which one. So here's equation 2, x minus 2y equals -3, and this really should be a y right there, right? But we know what y is. Y is 4. So let's plug in 4 and solve for x. So we have 8 minus -2 and 4 times 4 gives us -8 equals -3. And let's add 8 to both sides. What does that give us? X equals 5. So we have our x and our y, right? X is 5 and y is 4. All right, that's our solution. If we look at the graph, we can see that's the point where these two lines cross. We can see our equation 1, or a line 1. There's our second line, equation 2, and it says they cross at the point 5, 4, which is what we found algebraically. Hope this helps. This is, again, 2 examples of using the substitution method to solve a system of linear equations in 2 variables. If this was helpful, please subscribe to the channel, and thanks for watching. Have a great day.